Today we're going to look at some applications of quantization. Some applications of quantization. Now, what is causing quantization of energy? Yes? All right. So it's the wave nature of electrons or protons or whatever massive particles we're talking about, and the confinement. Confinement leads to quantization. Whenever we trap a particle in a fixed region of space, not let it go out, or there is a change in potential as I will describe, that leads to quantization. So confinement causes quantization. I hope you understand the meaning of confinement. When you confine something to a small region of space, that leads to the quantization of energies. And we've seen this for the infinite well. Now, in the infinite well, so first of all, I'm going to talk a little bit about, with the infinite well, the concept of Bohr's correspondence. This is a principle that connects quantum physics with the classical world. Now, what does that mean? Suppose I have an infinite well. The potential energies are going to infinity, and we know that the energies of the particle that is trapped inside this well, they are quantized. So I have the ground state and higher states, and so on. So this is my, let me call this E ket 1, E2, E3, and so on. Some En perhaps. And with each of these quantum states is associated a wave function. That wave function is 2 over L, where L is the length of this well, sine of n pi x over L. So corresponding to this energy, there is some wave function. That wave function looks like, so I'm going to draw another diagram that depicts the wave functions. So the lowest energy is a wave function that is just one lobe of the sine wave, one lobe, two nodes, one antinode. This is this function when n equals 1. Its quantum state can be represented by ket 1. Its wave function can be represented by this function with n equals 1. The next higher state looks like this. The next state looks like this, and so on. And then you take the modulus square of these to find out the probability density functions. Now, so what's the difference between the quantum and the classical world? Suppose my particle is in the energy E1. Just imagine a particle which is inside a box and it has energy E1 and it's moving around in this infinite well with, say, some constant speed v. Now this is a classical particle. Okay. Now these are two impenetrable walls for this particle. The particle moves, it tosses to and fro, it reflects off from this wall, comes back, and it keeps on this periodic motion. If this were a classical particle, where would you, if I were to ask you where is the particle, where is the likelihood of finding the particle, what will your answer be? The speed is constant and it's just moving around periodically. So if I were to make a plot, this is my x, L, and if I were to make a plot of the probability density, that is probability per unit length, If I were to talk about the classical particle, what will the probability density look like? If I take some narrow region in space, so if I just look at this narrow region in space of length delta x, what's the probability of locating the particle in this length? It's constant, right? So the particle could be here, it could be anywhere, and the probability of locating the particle in this length will be delta x over L. In fact, delta x over L, wouldn't it be? So it's just a fraction of this delta x divided by the total length. That's the probability. Correct? So, and this probability is a constant. And so what is the probability per, this is the probability in a length of delta x. So in this region, this is the probability of locating the particle, correct? It's just the amount delta x divided by the total length, because the speed is constant. Now, what is the probability per unit length, which is called the probability density? It's 1 over L. You divide this by delta x by this length, you get 1 over L. So inside the cavity, inside the well, the probability of locating a classical particle is just constant, because the particle is spending equal amounts of time everywhere in the well, because it's moving with constant speed. So its speed is constant. So the probability of locating a particle at some region depends upon how long does it spend there. But how long does it spend there depends, it's always going to be uniform because it's moving with constant speed. So this is 1 over L, the probability density of locating a classical particle inside an infinite well. But quantum mechanics tells us that the probability of locating the particle, the probability density of locating the particle is going to be the modulus square of this, if we're just looking at the ground state. And the modulus square of this is a curve like this. You just take the square of this. It's the square of this thing. What's the maximum here? 2 over L. 2 over L. Now, this probability of locating the particle, say in some region of space, let me take a narrow region of space, this region, delta x, is wildly different between the classical and the quantum regimes. The quantum regime is telling us that it's more likely to find the particle inside the median of the well, inside the middle of the well, and it's very less likely to find the particle close to the edges. But classically, you're getting a uniform probability distribution. This is how quantum mechanics is really different from classical mechanics. And if this were a quantum particle, the experimental results would corroborate this blue probability density function, which is the quantum probability density function. The particle is not a classical particle. So for these low quantum numbers, these low n's, does the quantum world appear totally different from the classical world. However, if I go to higher quantum numbers, with really high quantum numbers, what do these wave functions start looking like? Their internode spacing gets smaller and smaller. So if I were to draw the wave function for a kind of a high quantum number, suppose I draw the wave function for n equals 10. So it's a high, an excited state. Then there will be 10 lobes. Alright, so today we're going to look at some applications of quantization. Some applications of quantization. Now, what is causing quantization of energy? Yes? All right. So it's the wave nature of electrons or protons or whatever massive particles we're talking about, and the confinement. Confinement leads to quantization. Whenever we trap a particle in a fixed region of space, not let it go out, or there is a change in potential, as I will describe, that leads to quantization. So confinement causes quantization. I hope you understand. And the modulus square will look like this. Equal height, right? This is what the probability density function is going to look like. Closely spaced lobes, closely spaced sectors. And now if I were to compare this with the classical, so this is 1 over L, this is the classical result, it's still 1 over L, this thing 1 over L. And if I now look at the probability density function for the quantum state, since these lobes are squeezed together, the average of the blue curve will start looking like the classical result. So if you go to high quantum numbers, you will find out that the classical and the quantum regimes, they correspond to one another, they converge to one another. Large quantum numbers correspond to the classical world. This is called the Bohr's correspondence principle. So we only see quantum effects and manifest these quantum effects when the quantum numbers are really small. Yes, please.
Can you repeat what would be the average of the blue result look like?
The average of the blue will actually look like just 1 over L, because these are closely spaced lobes. So the overall height is 2 over L. This is 0. So the average of 2 over L and 0 is 1 over L. So on average, the blue curve, so if you were to find out the probability of locating the particle anywhere, the results will look very similar for the classical and the quantum world. Alright. So if you take a small region in space, say this region, and you find the probability of locating the particle in this small region, you take the integral of the blue curve between these 2 points, it's going to be 1 over L. Alright? Because you get a complete cycle in these small regions because the nodes are very closely spaced together. So you take any small region, any small strip in this graph, the average of that blue curve over that small region will be 1 over L. Because in that small region, you are taking the complete swing from 0 to 1 to 2 over L. And the average of that is 1 over L. Alright? So the blue curve on average starts looking the same as the yellow straight line. So for high quantum numbers, the quantum world starts looking like the classical world. And that's why in our real life, we do not see these quantum effects, because we're really dealing with systems that have high quantum numbers. Okay? This is the Bohr's correspondence principle. Now what I would like you to do, in fact, I'm going to talk about really interesting stuff today. First of all, I'm going to talk about the potential step. Because I want to talk about quantum mechanical tunneling, I want to talk about spectroscopy, I want to talk about covalent bonds today, a little bit about atomic orbitals. I have lots of things to talk about, in fact. So potential step. Suppose, first of all, I'm going to describe to you how to draw these. This pink curve represents how the potential energy looks like for a system. Suppose I have zero potential energy in some region of space, and all of a sudden I have a bump. So in some region of space, the potential energy of a particle is 0. All of a sudden it sees a bump. For example, an electron is moving in free space. All of a sudden it sees a plate that is negatively charged. So its potential energy goes up. So an electron seeing a negative charge, the negative charge wants to repel the electron. So if the electron wants to get closer to the plate, its energy must go up. So the potential energy goes up. Or an atom falling from some height. Here the potential energy is high, but when it falls down to the ground, its potential energy is lowered. So it sees a ramp of potential energy. So just imagine that we have a potential step. So here the potential energy is 0. This point corresponds to x equals 0. This is my x-axis. This height is V naught. Alright, so this is the potential landscape. Let's call this a potential landscape. This is the landscape of the potential. Now what happens if the particle has some energy? Suppose I inject a particle from the left, a massive particle, say an electron from the left, and it has some energy. Now that energy can be greater than V naught, or it can be smaller than V naught. Energy, by the way, is always conserved, whether you see a potential or you don't. Suppose, first of all, let's first suppose that the energy is greater than V naught. So the energy is somewhere, the energy level is somewhere here. This is my E for the electron that is injected into this potential landscape. Alright. Now we know how to solve the time independent Schrodinger equation. And we know, so this is the time independent Schrodinger equation, minus h bar square 2m, the double derivative of the wave function plus the potential energy wave function equals the energy wave function. Correct? This is the time independent Schrodinger equation. Okay? And I can take this potential energy to the other side of the equation. This is also correct. Yes. Independent. So this is the time independent Schrodinger equation. All right. So far we've solved this for the free particle only, in which the potential energy was 0. So here the potential energy is 0. So in this region of space with negative x, this term just vanishes. And we already know what the solution to the Schrodinger equation is in this region. It's actually A EI k1x plus B E minus I k1x, correct? Where k1 is, what is k1? K1 is, can you speak up k1 for me? 2m E square root over h bar, correct? Correct? This is the time independent Schrodinger equation. We've solved it already. Just ignore this part. In this part, this is the wave function. It's an oscillatory function. This and the modulus square will look like this. Equal height, right? This is what the probability density function is going to look like. Closely spaced lobes, closely spaced sectors. And now if I were to compare this with the classical, so this is 1 over L, this is the classical result, it's still 1 over L, this thing 1 over L. And if I now look at the probability density function for the quantum state, since these lobes are squeezed together, the average of the blue curve will start looking like the classical result. So if you go to high quantum numbers, you will find out that the classical and the quantum regimes, they correspond to one another, they converge to one another. Large quantum numbers correspond to the classical world. This is called the Bohr's correspondence principle. So we only see quantum effects and manifest these quantum effects when the quantum numbers are really small. Yes, please.
Can you repeat what would be the average of the blue result look like?
The average of the blue will actually look like just 1 over L, because these are closely spaced lobes. So the overall height is 2 over L. This is 0. So the average of 2 over L and 0 is 1 over L. So on average, the blue curve, so if you were to find out the probability of locating the particle anywhere, the results will look very similar for the classical and the quantum world. Alright, so if you take a small region in space, say this region, and you find the probability of locating the particle in this small region, you take the integral of the blue curve between these 2 points, it's going to be at beyond this point. So there's nothing that reflects the wave back. So this term is going to be 0. So here the wave function is this plus this, and here the wave function is just this part. And this k2, by the way, is a new wave number. It's just E replaced by E minus V naught. So this k2 is now 2m E minus V naught h bar. So now let's plot this. Let's plot these functions. Potential step V naught now the energy is bigger than the potential step. So now this wave function, these wave functions, they are complex. I can't plot complex wave functions. So let's just plot the real part. So the idea is that this is going to be a wave. Of course, this is going to be a wave in which B and A are related, but it's not going to be a standing wave. But the important thing is the wavelength or the wave number. That's k1. This is this thing, 2m E over square root over h bar. Here the wave number changes, k2 changes. It's now E minus V naught. So which k is bigger? K1 or K2? K1 is bigger. Which wavelength is bigger? This wavelength is bigger. So the wavelength is smaller here. The wavelength is larger here. So if I were to plot roughly the real part of the wave function, it's going to look like this. Here the wave number is k1 is 2me over h bar. Here it is, the wave number is smaller, which means the wavelength is longer, because the wavelength is 2 pi over k. Okay, so here it is, k is 2m E minus V naught over k h bar, and the amplitude remains the same, because really it's not a bound particle, it's just seeing a potential step. It's not a bound particle, so the amplitude remains the same. Though, now the question is, so far so good. Do you get this point? We can also imagine that if this were my energy of the system, sorry, let me draw a straight line. In this region, the potential energy is 0. So what does this height signify? What is this height equal to? Total energy minus potential energy, which is kinetic. So this is the kinetic energy in this region. Let's call it T1. Large kinetic energy. Large kinetic energy means large energy. Large energy means large momentum. Large momentum means short wavelength. De Broglie principle. Here, the kinetic energy has gone down, but the kinetic energy, by the way, is still positive. It's still positive, right? Because this E is bigger than V naught, and that smaller kinetic energy leads to longer wavelengths now. So this is the wave function for a single particle that encounters a potential step. And all right, and we can also look at this in a different way. A particle comes in, it has some probability of being reflected from this potential step, and has some probability of being transmitted. Now, if I look at these coefficients, what should be the probability of reflection? Can these coefficients tell me somehow reflection? B over A modulus square, right? So the reflection is B over A modulus square. And what about the transmission? C over A? Only C? I mean, it has to be normalized with respect to A. Everything is normalized with respect to A. How many particles are coming in and so on. So if I were to calculate B and C in terms of A, let's try to do that. So how can I calculate A, B and C? Is there anything inside this system, inside the quantum system, that can help me calculate these coefficients? Anything? Boundary conditions. So first boundary condition at x equals 0, the wave functions must match x equals 0. So at x equals 0, what do I get at x equals 0? What is the psi 1 at x equals 0? If I put x equals 0, what is the first wave function? A plus b. What does this equal to? C. This is my first equation. What's the second equation? I take the derivatives of the wave functions. They must also be equal at x equals 0. So what's the derivative of the left hand side of the first wave function? ik1 a minus b. This gives me ik2 c, right, at x equals 0. But k1 is not equal to k2. So this means a minus b equals k2 over k1 c. So now I have two equations. If I solve these equations simultaneously, so let me subtract the two equations. I will get 2b c 1 minus k2 over k1, which means this is c k1 minus k2. This means my b equals c over 2 k1 minus k2 over k1. And if I were to add the two equations, so let's call this equation number 1. If I add the two equations, I have 2a equals c k1 correct? Now what I could do, I could first of all, if I want to find b over a, so this to the other side too. B over A is K1 minus K2, K1 plus K2. Got it? And the probability of reflection. Yes, please.
Sir, how did you get that equation from the derivative?
This one? So the derivative of this function here is I k1a ei k1x, k1 at x equals 0, the exponential factor goes away, so I'm left with I k1a. Likewise for this. Okay? So the reflection coefficient B is the probability amplitude of reflection, but it's a probability amplitude. In order to find out probabilities, you want modular squares. So it's just going to be the modular square of this thing. Correct? नहीं समझ आ रही? कहाँ से नहीं समझ आ रही? इसकी समझ आ गई? इसकी नहीं आई? आ गई? So these are the two wave functions. What's the derivative of this wave function? The derivative, let's call this psi 1. This is psi 1, this is psi 2. Alright? So the derivative of psi 1 is I k1 a e I k1x plus I k1 a b, this one minus e minus I k1x. If I put x equals 0, what do I get? I k1 a minus I k1 b. See? इसी तरह right hand side. Yes. Because we have properties that psi is continuous and the first derivative is also continuous. Remember from the infinite well. So now this term gives us the reflection coefficient, which is just going to be the square of this. All right. K is real, so I just don't need the modular square, just the modular square. So when a particle sees an infinite well, sees a potential barrier, a step, it is reflected back with some probability. And that probability depends upon K's, and the K's depend upon the height of the gap. Because each K depends upon what the potential energy step is. By the way, is there anything in your classical world, in normal physics, that kind of resembles this? Yes? किसने बोला है? कौन बोला है? Excellent. When light in air or vacuum shines on a surface, it sees a potential energy gap, a discontinuity, and it reflects back. And the amount of light that reflects back is exactly given by n1 minus n2, n1 plus n2 whole square, where n's are the refractive indices of the two mediums. So this is exactly the same result for normal incidence of light. By the way, can I calculate the transmission coefficient? So how can I calculate the transmission coefficient? The transmission coefficient T is a probability that a particle comes in, sees this potential well, and is transmitted. It must be 1 minus this thing. All right. And I've used some process to calculate T. Can I find out T from first principles as well, from these amplitudes. So here I've defined my reflection to be B over A squared. What will my transmissivity be? C over A squared. So your proposal is C over A squared. Is that correct? Well, it's not totally correct. If you find out C over A, first of all, you can find out C over A. That's pretty easy. C over A is 2k1 k1 plus k2. But you will find you square this, that's not 1 minus the reflectivity. So there's something else going on. You need an additional factor. Can you guess what's missing here?
Is it a factor of 2?
Not a factor of 2. What's missing here?
An absorbance factor.
There's no absorption. We're assuming there's only reflection and transmission. Well, imagine electron is a charged particle. Let me give you a hint. An electron is a charged particle. Suppose it sees this, it encounters this potential discontinuity. Now, when a charge moves, what is it called? Current. Now, when current comes in to this potential well, there's some likelihood that the current will be returned, and some likelihood that the current is going to go forward. Is current conserved? Current is conserved. If there is no charge deposition on the surface, whatever current comes in a node must equal to all the current that goes out. So now there is some current that is being reflected. This is the reflected current, but this is not the transmitted current. So how do you find out the transmitted currents? K1 plus K2. G? Kirchhoff's law. So the Kirchhoff's law, first Kirchhoff's law states that current coming in must equal to the current going out. So we really need to find out the current going out. For transmissivity, we need to find out the current coming in, hitting the barrier, and the current that is being transmitted. Now, does current have anything to do with speed? Yes. So speed is v. Does speed have anything to do with momentum? Yes. So what we need to find out is the transmitted current. Transmitted current. Let's see what the transmitted current is going to look like. The transmitted current is the probability C modulus square multiplied by the speed with which that particle moves in the second medium. Any current, I take a wire. If I were to take a wire, there is some charge Q that is, Q is a charge on an electron, all right? And then if I were to find out the current, what is the current charge per unit time? Right, the charge per unit time. Now if this distance is L, this cross sectional area is A, then this volume is A over L, and if I have n charges in this area, the total charge in this area is Q times n. This is charge per unit volume. I multiply this with, okay, let's call this, I multiply this with AL. This is the total charge in this section. Now I need to find out the time. So if I were to multiply this with V and divide by AL, this will give me the current density, the charge per unit area. So also the current per unit area. So the current per unit area is given by Q N V. So any current can be found out by multiplying the charge per unit volume with the speed. Charge per unit volume into speed. Speed is distance over time. So this becomes charge into distance into area. Volume is distance into area into distance over time. Right? So the distance just cancels out. This is charge per unit area into one over time. This is charge over time is current. So this is current per unit area. Okay, so this is our formula. The current per unit area is this. So now I'm dealing with a one-dimensional system. So really I need to have length instead of area. But the point is that this current over area, this is current over area, this is this thing multiplied by the speed. So the speed factor has to be taken into account. So the charge per unit volume is kind of the probability density. The charge per unit volume is the probability density. What's the probability of locating the particle in a certain amount of length? Replace the volume with the length because we have one dimensions here. So this is the probability density multiplied by the speed. So the transmitted current is C, which is the probability density on the left, on the right of the barrier multiplied by the speed. But what is the speed? The speed is momentum divided by the mass. The momentum is h bar k2 over m, correct? So this is the speed of the particle in this region. In this region, the speed is h bar k2 over m, correct? What's the speed here? H bar k1 over m. So the outgoing current is this thing, and the incoming current is A mod square into H bar k1 over m. So the transmission coefficient is the ratio of these currents. Okay, in quantum physics these are called probability currents. So the ratio of these means that you really have to multiply this with h bar k1 over m and divide by h bar k2 over m. Now the m's go away, h bar goes away. This is your transmissivity. So you multiply C over A mod square with k1 over k2. Here you can also kind of do the same thing over here, but in this region it's in the same medium. So there's a velocity k1 in the numerator and a velocity k1 in the denominator as well, and both of them cancel out. So if you use this formula for the transmissivity, it will turn out to be 1 minus r, or in other words, the reflectivity plus the transmissivity is 1. Yes, please.
Sir, so the transmitted current and वैसे पहले equally C नहीं होना चाहिए क्योंकि there's some inefficiency.
So some of it is being reflected. So some current is coming in, some of it is being reflected, the rest of it is being transmitted. So this is the ratio of the transmitted and the incoming current. 1 minus this will be the reflected current. Any questions about this? Sorry, K2 over Q1. Sorry, K2 over Q1. Sorry, thank you. This will be a homework problem. Now the point is, what if the potential landscape looks like this? The potential energy is 0. All of a sudden, there is a drop in the potential, and that drop is V naught. Will there be some reflection?
Yes.
There will still be some reflection and some transmission. Now the kind of strange thing here is the potential energy is dropping. The particle is coming in. When it sees that potential energy dropping, there's still some probability of it being reflected, which is kind of counterintuitive from the classical perception. And if I were to draw the wave function, can anyone come to the blackboard and draw the wave function? The energy is still greater than all of the potential energies. This is my energy. Can you draw the wave function? The real part of the wave function? Yes, please.
सर किधर ड्रॉ
इधर ही कर दो, इसके ऊपर ही. Carefully. Excellent. Beautiful. So here K is small because the kinetic energy is small. Here the kinetic energy is large. So K is large kinetic energy means small k. Here K is large, small wavelength. Alright. So higher the kinetic energy, smaller will be the K, smaller will be the wave number. Alright. So this is an accurate representation, at least what you can do by hand, of what the wave function is going to look like for this free particle that now sees a potential discontinuity. That discontinuity can be up or down, and there will always be some reflection and transmission. But the really interesting scenario is, if in this potential step, so let me draw another potential landscape. A step of height V naught. Here the potential energy is 0. But now an electron is again injected. Now this is something really interesting. You will not find this anywhere in classical physics. Suppose I have an electron whose energy is now less than V naught. This is my energy E. Now imagine a person moving with some energy, and he has to climb a mountain or a hill, and the person doesn't have enough energy to overcome that energy barrier. Classically, this particle cannot be transmitted. It cannot penetrate into this region. This region onwards is classically forbidden. Because here the total energy is less than the potential energy. So kind of kinetic energy becomes negative. It doesn't really make sense. However, let's look at the time independent Schrodinger equation again. Here in this region, the wave function remains the same. A EI K1x plus B E minus I K1x. Here, suppose it is CEI K2x. Alright. Now, in this region, now K1 here is exactly the same as this K1, this thing. K2 is also the same. The only problem is that E minus V naught is now negative. So in this region here, in the classically forbidden region, this is now, K2 is now under root 2m E minus V naught over H bar. Previously E was bigger than V naught, so you can take the square root. But now in this region, since the energy of the incoming particle is now smaller than the potential barrier it has to overcome, this term becomes negative. And when it becomes negative, what's the square root of a negative number? Iota. So what I could do, I could write this as iota 2m V naught minus E over H bar. Correct? Now this V naught minus E is positive. I can do that, right? Let's call this thing alpha. So I can write this as I alpha. Alpha is now a real positive number. I alpha is complex. Correct? So now this thing becomes C E I alpha x. This becomes C E minus alpha x. Now this is not an oscillatory function. It does not have an iota part in it. What does this function look like in space? E raised to minus alpha x. It's an exponential decay, isn't it? My friend, you getting it? It's an exponential decay. It does not have an iota in it. So now if I want to plot the wave function, let me give it a shot. Here the wave function is this, it's oscillatory. This is my zero line. This is 0. So this is, pink is now representing the wave function. I'm drawing many things on the same graph. The yellow and the white, they represent energy. But now I'm on the same graph, just to superimpose what is happening in the landscape, I'm drawing the wave function. Now if at this point this becomes the wave function, respecting the continuity of the wave function, from this point onwards I have to plot this thing. Now what does this thing look like? It's going to be an exponential decay towards 0. It's going to be exponential decay. But let me zoom in onto this region. Let me zoom in onto this region. Physically, this region is classically forbidden. There is no likelihood. The particle cannot enter this classically forbidden region. It's impenetrable. This wall is impenetrable for the particle because it doesn't have enough energy. It's just like having, this is my hill. An object of energy E comes in, this height is h. If this E is less than mgh, this object cannot get here, cannot get up to the summit of this hill without additional fuel or without ramping up its energy somehow. And there's no chance that it can be found on the other side of the hill. This is classically forbidden. Quantum physically, it is possible. Yes, please.
So exponential function, won't it just keep going on?
I mean, it just goes asymptotically to very small numbers, very small numbers. So I'm going to zoom in on this region. So my eye is on this region now, right? Here is my eye. So let me zoom in onto this region. You will not see these effects in the classical world, but you see them in the real world. So now if this is my wave function, this is the zero line. Now this wave function here just exponentially decays. It doesn't oscillate, it just decays. How much does it now it penetrates into the classically forbidden region. It penetrates, it does go there. There is some likelihood of finding the particle inside the classically forbidden region. Now I can define a penetration length. So how far does it extend into this classically disallowed region? It depends upon alpha. Alright, it depends upon alpha. So this function here is e raised to minus alpha x. When x is 1 over alpha, this number becomes e raised to minus 1. This is about 0.37, I think. So when x equals 1 over alpha, this wave function will have dropped to 37% of what its value were here. Okay, and then by the way, this is the wave function, not the probability density. So this 1 over alpha is actually telling you how much this particle can go into the classically forbidden region. So 1 over alpha, I can define my penetration length to be 1 over alpha. That 1 over alpha is h bar 2m v minus e naught, v naught minus e. Yes, ये वाला, ये वैल्यू डालो ना, इसको कैलकुलेट कर लो. ये this, where do we get this from? We get this from here. किधर गया? ठीक. So this is the kind of penetration length. So if I want to make this penetration length longer, what do I need to do? I need to make this thing smaller, which means if my E is very close to V naught, then the penetration length can be large. And since this is exponential, it is ultra sensitive dependence upon the difference between V naught and E. I will probably give some numerical simulations for you to do in a homework problem. So this is called the penetration length. Now the key point is that even inside this classically forbidden region, the wave function is leaking into it. The wave function is found in a otherwise classically forbidden region. But the extremely interesting thing happens when I have a scenario like this. When my potential landscape looks like this: 0, step, step down, what if I have a potential hump, just a hump like a speed breaker for this particle? Now this is my V naught, and if I were now, I have 3 regions now left inside this barrier here. My total energy, suppose, is less than V naught. This is my total energy. Now there is not enough energy. A particle is coming in from the left. There is not enough energy for the particle to go beyond and be found in this region, because it cannot overcome the potential barrier, because this is really high. However, this phenomenon, you can solve the time independent Schrodinger equation. If you are brave enough, you can also do the calculations, easy to do but very cumbersome and tedious, but you can find this in any standard book on modern physics. If I were to plot the wave function, oscillatory here, with a k1 that depends upon this, the energy of the particle, decay here, non-oscillatory here. But then in this region, if this width w is not big enough so that the wave function has not totally decayed, or this energy is very close but still smaller than the height of this bump, there will still be some non-zero wave function that is reaching the second edge of this potential barrier. And since the wave function must always be continuous, it's now going to be oscillatory. Same wave number as here, but probably a diminished height. So this is how an object can surpass classical barriers and go beyond the veil. Look, it can see beyond the curtain. There's nothing impenetrable for this particle if this width is small enough. This phenomenon is called quantum mechanical tunneling. And you can find out the probability for this tunneling as well. Now you have a function here a plus b something c something d here. You have 4 coefficients. This is called quantum mechanical tunneling. Quantum mechanical, the energy of the particle, by the way, remains unchanged. Whatever the energy is here, it's here. It's not that if I am climbing, I climb this, I waste some of my energy climbing it, and then I'm exhausted and I'm kind of walking on the other side with less energy. It's not like that. The particle, it overcomes this barrier and doesn't change its energy. This is quantum tunneling. So now the question is, now Dr. Sabieh, you're kind of, this looks paradoxical, because if tunneling would happen, is there a probability of locating the particle inside this classically forbidden region? Answer yes or no. Sometimes you should see the particle inside this classically forbidden region. But the problem is that you'll never. Even though the particle has gone beyond, and you can find the particle with some finite probability here or here, you'll never be able to locate it. You'll never be able to situate it inside this barrier. Why? Let's give this chance to someone else. Yes, please. No, but it's bigger than this. The wave function is bigger than the wave function here. Because yes, please.
Is it instantaneous?
It is instantaneous, but everything is instantaneous. Yes, please.
Because negative kinetic energy is that to be that.
Yeah, but when you get tricky answers of this kind in quantum physics, always think about Heisenberg. The uncertainty principle doesn't let you locate the particle here, because this is the uncertainty in the position delta x or this delta. Let's take this to be your kind of uncertainty in the position, because if this were the penetration length, the particle, suppose it were to be found, the uncertainty in its position would be this much. So the uncertainty in its position delta x is about delta, which is h bar over 2m v naught minus e. Now delta p must be greater than or equal to h bar over delta x. If I'm ignoring the factors of 2 and 1 over 2 and so on, because they don't really matter. Now if this is, which means that delta p must be greater than this thing, the uncertainty in momentum, which means that the momentum must be at least as big as the uncertainty in the momentum, right? You can't have momentum which is smaller than the uncertainty in the momentum. So this p minimum for the particle, if it were to be located in this narrow region, has to be equal to this. This of course is equal to 2m v naught minus e. Now this is my minimum p with an root. So what is my minimum energy for this particle? If my particle is to be located in this small region, its energy takes up a minimum value. Remember 0 point energy? What is that energy? That energy is p square over 2m. This p minimum square over 2m, which is now v naught minus E. But v naught minus E is simply this much. This is v naught, this is E, so this thing is v naught minus E. So the energy of this particle must at least be, it must have a kind of fluctuation over this value which is bigger than v naught minus E, which takes it out of this well. So when you try to squeeze the particle, its energy goes up, and the energy is so large that it becomes bigger than the potential barrier, and it just pops out of this region. You can't locate it inside this region. That's why it's impossible to locate the particle in these small barriers. But nevertheless, you can find the particle on the other side. Just imagine this table is my barrier. I can locate the particle here, and it's moving, it's traveling, and I locate the particle here. And this transit here does take some finite time. It's not instantaneous, it does take some finite time because the particle after all is moving with a small speed. But I'm never able to locate the particle here. It's either on that side or on that side. This is called quantum mechanical tunneling, and it has profound consequences in physics. In fact, all covalent bonds are due to quantum mechanical tunneling. Now let me give you some more examples here. Yes, please. Physically नहीं होता particle. उसकी ये नहीं हम कह सकते. This is the wrong question. Yes, please.
So technically, could we look beyond the boundary if we really want to look for the particle? Is that even possible?
Yeah. You can look at the particle here. So this is
Yeah, beyond potential boundary.
Let's talk about this. I do not fully understand the question. Any more questions? Yes, please.
You can't, when you try to squeeze the particle in that region, you can't locate it because with the energy would be
The energy fluctuation would be so high that it's going to jump out of that region. Alright, you say that the atom is mostly empty space. If you look at the Bohr's model, you see that the atom is empty. But quantum mechanically, if you invoke the uncertainty principle, you cannot squish an atom. You cannot squeeze an atom. Because if you squeeze it to really small sizes, the energy goes so big that it becomes bigger than the ionization potential for that atom, and the electron just flies away. So you cannot squeeze atoms because of the uncertainty principle. The uncertainty principle really puts a limit on many things. Alright, so whenever you don't know an answer to something, think about the uncertainty principle. Whenever your multiple choice question gets wrong, think about the uncertainty principle. Now let's look at a few more examples of this really confounding phenomenon. But before I'm able to do that, let's some examples from inside a well. Suppose I have an infinite well. Of this kind. Now it's an infinite well, but inside the well there is a potential discontinuity. Okay. Now we do know that the energies will be quantized. If I were to, and I'll give you some problems of this in your exams as well, so think about this carefully. If I want to find the wave function for a particle inside this well, I don't need to solve the Schrodinger equation and do all of it. I can do it graphically. Suppose I care about n equals 4, the fourth level, the third excited level. Now this has kind of 4 lobes, 2 complete sine waves normally. But now, and the energy of the particle is this much. So this is V naught. This energy at all times is bigger than V naught. And I want to find what the wave function, I want to plot what the wave function looks like. Now the wave function, the kinetic energy is large here, the wavelength is smaller. Here the kinetic energy is small, the wavelength must be longer. Speed is also small here. So if I were to, so small wavelength, I want small wavelength here, large wavelength here. So yeah, एक मिनट. ठीक है. Small wavelength, large wavelength. Still 4 lobes, 1, 2, 3, 4. Small wavelength, kinetic energy is large, T is large, E minus V naught is large, which means K is large, which means lambda is short. Here the opposite is true. The kinetic energy is short this much, which means E minus V naught is small, which means K is small, which means lambda is long. But the question I would like to ask you is, why are the amplitudes different? Why do we have a bigger amplitude in this part of the well? Not uncertainty. What is the reason? Is the particle moving with uniform speed even classically? No. Here the speed of this particle, since the kinetic energy is small, the speed is small. And when the speed is small and you look at the particle, since the speed is small, is greater likelihood of locating the particle in the right side of the well because it's moving slower. Remember musical chairs? You are likely to hit upon chair when you move slowly towards it. So the particle is moving faster here, and when it reaches the right side of the well, it gets slower. So if a random observer were to locate the particle inside the well, there's a higher likelihood that it will be found in this region. Therefore, in this region, the wave function has a bigger amplitude, and likewise the kind of probability amplitude looks like this. The probability density function or the modulus square of the wave function looks like this. What if an atom, suppose an atom is falling from above the ground, this is the ground, and now I have an atom which is a quantum particle, and I want to associate a wave function with this particle. It's falling towards the ground. This atom has some mass. Every atom has some mass. What will be the wave function of this particle look like? And by the way, there are real experiments in which you drop particles. Those particles are called atomic fountains. So can you kind of plot the wave function on this axis? What will it look like? Can you please plot this? Or for convenience, plot it like this.
It just keeps on getting smaller. Keeps on getting smaller.
Exactly. So, but more, it would actually look more. So the kinetic energy is larger here. So shorter wavelength. So it's just going to probably look like this. All right. So So now I'm plotting the wave function. This is my plot of this is my z axis, and this is the wave function, okay, psi of z. Okay, so this is the wave function for a dropping atom that drops down. All right, now we have still 10 minutes to go. Any questions about this? So I'd like to give you some example on nuclear physics.
Sir,
Yes, please.
so
The amplitude is changing because the particle is slower here, faster here. When it's slower here, there is a higher likelihood of locating the particle here. If a random observer looks at a particle, opens up a shutter, so it's more likely that the particle will be found here. That's why the amplitude is larger, because the amplitude square gives you the probability of locating the particle somewhere. Now, nuclear physics is really interesting. Tunneling is not something in the books. Tunneling is everywhere in our lives. Radioactivity is quantum mechanical tunneling. We can build devices out of quantum mechanical tunneling. People argue that it has a role to play in hereditary processes as well. It's always there in your chemical dynamics and so on. Electron radical transfer and proton transfer in a photosynthesis reaction depends upon quantum mechanical tunneling. So it's there. Now let me give you an example. If I have, let's talk a little bit about radioactivity. Now, what is radioactivity? A nucleus. Probably the only time you're going to see nuclear physics in this class. A nucleus, big nucleus, disintegrates and gives rise to, say, an alpha particle. All right. Now, let me write down a nuclear reaction. Uranium 92, 238. This decays. This nucleus is radioactive, naturally radioactive. It decays with a half-life of about 1 billion years. Now this decays, gives you thorium, another nucleus, 90, 234, and releases an alpha particle. This is your alpha particle. The alpha particle are 2 protons and 2 neutrons. Alright, so what really holds a nucleus together? I need to find out the potential landscape. When I want to talk about tunneling, first of all, I need to identify the potential landscape. So what holds a nucleus together? A nucleus has many protons in it, and they're all positively charged. So when you bring all these 92 protons together, they must repel one another. Right? So the energy must go up. If this is the case, a nucleus will never be able to form because of these strong repulsive forces. Now, if you look, if I want to make a diagram, distance, energy. Let's call this the energy V. Depends upon the distance. If I bring, let's consider 2 protons. If I bring 2 protons together, will the energy go up or down? Up, because you're moving against the repulsive force. So the energy keeps on going up. This also comes from Coulomb's law. The energy here is Q1, Q2 over 4 pi epsilon naught R. R is the distance between the nuclei. You squeeze the 2 nuclei, the 2 protons together, the energy keeps on going up. But if this is the case, a nucleus as big as uranium will never be formed. A nucleus as big as iron, nickel, manganese will never be formed. But nuclei are stable up to a certain atomic number. But what keeps the nucleus together is the process. So what kind of force is this, by the way? Can you tell me what kind of force is this? It's an electrostatic force. So this potential energy is due to electrostatics. So this is an electrostatic force. Now what holds this nucleus together is another force. When you get to very small distances at the size of the nucleus, which is about 10 femtometers. Femto is 10 to the power minus 15 meters. A new force kicks in. A new short range force kicks in. It's called a strong nuclear force, and that is attractive. Alright, so there are four fundamental forces, right? This is one of them: strong nuclear, weak nuclear, electric, magnetic, and gravity. So this is a strong nuclear force. It kicks in, and this is attractive. So it lets the nucleons coalesce. It lets them come together, and the energy suddenly drops. But this force is only operative over these small distances. So this L is roughly 10 femtometers. Now imagine this radioactive process. This is a uranium nucleus. Where is this alpha particle coming from? It's coming from inside the nucleus. So it's a big nucleus, a parent nucleus, and two protons and two neutrons decide to migrate, emigrate in fact. They want to leave the nucleus and come out as a radioactive particle. So now what those alpha particles are inside this well. This well is like an infinite potential. Alright. Now if they so this is your alpha kind of alpha nucleus. It's inside the big thorium nucleus. So this is a big thorium nucleus. The alpha particle is residing inside it, and it's inside this infinite well. Right? How big is this well? How big is this? Can you estimate the height of this? How much energy would this mean? Is there a way to do that? Can you do a calculation and tell me how big is this energy? The answer lies here. Take R to be equal to 10 femtometers, Q1 to be the charge on a helium nucleus, which is two electron charges. This is the charge on a thorium nucleus. So this is 90 times 1.6 into 10 to the power minus 19 coulombs. This is 2 times 1.6 into 10 to the power minus 19 coulombs. You know this constant 1 over 4 pi epsilon naught, it's 9 to 10 power 9. Put R equals the size of this infinite well. You will get an estimate of this energy. This energy is roughly, if you calculate it, you can do this in a minute. This turns out to be about 30 mega electron volts. Mega electron volts. For 1 electron volt, you already know what 1 electron. But the alpha particle that comes out from this nucleus is a mere 4 mega electron volt. So if this alpha particle comes out from this nucleus, it's a mere 4 mega electron volts. How do you know? Because we can measure the energy of alpha particles that come out from radioactive sources. Those alpha particles are measured to be around 4 mega electron volts. Now, how does a particle of energy 4 mega electron volt muster enough energy to overcome a barrier that is 30 mega electron volts. It tunnels out. It can't do so classically, just tunnels out. So in fact, so radioactivity is tunneling. This is quantum mechanical tunneling. This nucleus just comes out and kind of moves away. It's due to tunneling. In fact, inside a nucleus, we can model a nucleus by an infinite well. And if you take two neutrons inside the nucleus, suppose when they are free, the energy is given as 0 mega electron volts. But you have these kind of energy states inside the nucleus. Just like an atom, you have energy states inside the nucleus. This is called the nuclear shell model. But the gaps between these energies, in a hydrogen atom, how big are the gaps? How big are the energies? Tens of electron volts. 13.6 electron volt is the minimum energy. That's the ionization potential of hydrogen. 13.6, 10, 7 electron volts. So the energies in the hydrogen atom for the electron are just electron volts. But these energy gaps are in the mega electron volts. Why is that? Kind of, but it's because of the small size of the nucleus. Small size of the nucleus causes a fanning out of the energies. Minimum energy is given by n square, h bar square, pi square, 2ml square. What's the size of a hydrogen atom? Half a nanometers. What's the size of a nucleus? 1 femtometer. 6 orders of magnitude smaller than a hydrogen atom. So when this is 6 orders of magnitude smaller, the energies will be in the mega electron volts regime. So if a transition takes place inside a nucleus, say from here to here, and a photon is emitted, this photon is going to be in the mega electron volts regime. Very short wavelength, high frequency, very high frequency short wavelength, and these photons will be gamma ray photons. So this is how you produce gamma rays from inside the nucleus. It's coming from an infinite well. Gamma rays are coming from an infinite well. Alpha particles are coming from radioactivity, which has its origin in quantum mechanical tunneling. There will be no medical physics without radioactivity. No therapies, no diagnostics, no gamma ray knives, no positron emission computed tomography, no PET scans, no medical diagnostics without quantum physics. There will be no MRI without quantum physics. It's all real. Finally, I just want to have one more point in the next class. Bonds are formed because of tunneling. You will have no molecules if there were no tunneling. By the way, on Tuesday we're going to have a quiz. That's the anticlimax. Topics from homework 3.